Hello, welcome to another module in this massive open online course. So, we are looking at various convex optimization problems and especially focusing on their practical applications. All right, we are looking at this from an applied perspective. All right, in this module, let us look at another interesting problem with a very important and I would like to say novel practical application, that is of beamforming in MIMO systems. So, what we want to look at in this module is the problem of MIMO now. What happens in a MIMO? Now, what we have looked at previously we have seen only multiple antenna previously we have seen when you have multiple beamforming, when you have multiple receive antennas. Okay. You might recall that we consider a system which is modeled as y bar equals h bar times x plus n bar, and then we derived the beamformer for this system. The beamformer for this system is given by w bar equals h bar divided by norm of h bar. This is termed the MRC, or the maximal ratio beamformer, okay, the maximal ratio combiner. We have seen this before. Now, what we want to do is we want to extend this to a MIMO system. Remember, you might recall MIMO system is a system which has not just multiple receive antennas, but also multiple transmit antennas. So, you have multiple antennas at the transmitter as well as the receiver. That is why it is known as a MIMO system, or a multiple input multiple output system. Okay. So, what we want to consider is this interesting problem of beamforming, and this is not so trivial, straightforward. Beamforming for MIMO, okay, which basically simply stands for multiple input and multiple output. Multiple input, which basically implies that you have multiple transmit and multiple receive antennas, multiple TX plus you have multiple RX antennas, multiple receiver. You have multiple transmit and multiple receive antennas, and one can represent the system. Let us just, so you have, let us say this is your transmitter, you have multiple transmit antennas, and at the same time you have multiple receive antennas. Now, these need not be equal, okay, and this is your transmitter, this is your receiver, and you have the different possible paths, you can say, or links between the trans. So, you have, let us say, T antennas at the transmitter, these are your T transmit antennas, and these are your R equals the number of receive antennas, and this is your transmitter, this is your receiver, and the system model can be represented as follows. Your received vector of symbols y1, y2, up to YR. Since there are R receive antennas, you are going to have R received symbols Y1, Y2, YR equals H, this is your channel matrix, times X1, X2 up to XT, because your T have T transmit antennas, therefore you can transmit T symbols plus you have your noise vector. Now as you can see, this is Y bar which has R symbols, okay, which is basically R cross 1 vector. This is X bar which is T cross 1, that is it has T symbols because you have T transmit antennas. And now naturally you have R dimensional output, T dimensional input. So the channel matrix that transforms the T dimensional input to R dimensional output, this is the R cross T. This is known as the H equals the R cross T, that is R rows and T columns in the MIMO channel matrix. So this is your R cross T MIMO channel matrix, and N bar, that is the noise vector, this is an R cross 1, this is an R cross 1, this is an R cross 1 noise vector, okay. And what we want to do is we want to explore how can we use beamforming. Remember, beamforming means transmitting in a particular direction, that is focusing the transmit power in a particular direction, and receive beamforming means focusing, that is looking in a particular direction to receive the maximum amount of energy. That is what we mean by beamforming, alright. So beamforming in a multiple antenna system, remember, that is basically you are looking in a particular direction, and at the transmitter also you are transmitting in a particular direction. So this is your transmit beam, so as to speak, and this is your receive beam. Now there can be multiple beams, but when people talk about beamforming, they typically talk about a single beam. So you have a transmit beam, that is you are focusing the energy in a particular direction, and you have a receive beam, that is you are looking for the signal, that is you are receiving the signal in a particular direction. By doing that, you are achieving several things, as we have seen in multiple antenna beamforming. That is, one is you are maximizing the signal to noise power ratio. Two, by using only a particular direction, you can avoid the interference, that is the interference which is caused by the interfering users. By avoiding those other directions, you can basically suppress the interference at the receiver. So beamforming has many uses and it's very useful practically. Okay. Now how do we do beamforming in a MIMO system? That is what we want to explore. So let us say we want to transmit the vector x bar, we want to use a beamforming. Remember, beamforming vector is central to the idea of beamforming. So this V bar, this is the vector of, so this is your beamforming vector, and this is more specifically, since you are doing this at the transmitter, this is also known as the this can also be known as the transmit beamformer or the transmit. So what you are doing is you are using V bar at the transmitter, alright, to focus the energy or transmit the energy or transmit the signal in a particular direction. This is known as transmit beamforming, and this V bar gives the transmit beamformer, okay, and X is the transmitted symbol which is transmitted with the aid of this transmit beamformer. Remember, this is the concept of electronic steering, where you are adjusting the weights such that you focus the signal in a particular direction. Okay. So V bar X, this is the transmit. Now what we can have the transmit power equals, can be P, that is this is the transmit power, so now the beamformer itself, it simply focuses the signal, therefore it should not amplify or attenuate the signal. So what we will do is we will fix the power of the beamformer, that is norm beam W square. So the transmit power is fixed. So the energy of the beamformer, this norm VW bar square is fixed. So that basically this imposes a transmit power constraint. So, transmit power is limited to P. So, this limits the power that has to be transmitted. So, this is also known as the transmit power constraint. So, norm V bar square equal to 1. Okay. So, this to basically this constraint is to limit the transmit power. We want to limit it to a limit it to a unit norm beamformer. Okay. So, now remember we have this system model here, which is basically your y bar equals h times x bar plus n bar. This is your MIMO. This is your MIMO system model. Now, what we want to do is we have y bar equals h x bar plus n bar. Now, here we want to substitute x bar equals v bar times x, that is what we said. V bar is the transmitted beamformer, x is the transmitted symbol, V bar is a transmitted beamformer, x is the transmit symbol, and therefore, now this is going to be h times V bar x plus n bar. All I am doing is instead of x bar, I am substituting x bar equals V bar times x. So, this is y bar. Okay. And now, what we are going to do at the receiver is at the receiver we are going to employ a combiner. So, this is your received symbol vector. At the receiver we employ a combiner. Now, at the receiver one can employ a combiner which is of the form, that is, you perform u bar Hermitian y bar. So, this is basically your receive beamformer. Now, this becomes your u bar equals your well, you can think of this as the receive filter you are combining with u bar. So, you are performing u bar Hermitian y bar. Okay. And also we can restrict without loss of generality, we can restrict norm u bar to 1, that is the norm of the receive beamformer is also being restricted or limited to 1. Okay. And therefore, now if I substitute this model, I have u bar Hermitian y bar. Now, I am going to substitute expression for y bar equals u bar Hermitian h x bar plus n bar equals u bar Hermitian. Now, h x bar, of course, x bar we have replaced by h times v bar into x plus n bar, which is now, if you simplify this, this is u bar Hermitian h v bar into x plus u bar Hermitian. Okay. And now what we have to do is we have to determine both u bar and v bar, that makes. So, this is my receive beamformer and this problem is challenging because you can see you have to determine not one but two beamformers. So, this is your beam for receive beamformer. This is your transmit beamformer, And so now we have to jointly, so now what is the problem in MIMO beamforming? We have to jointly determine both Rx and Tx beamformer, that is U bar and V bar to maximize the SNR. Alright. So, what we want to do is basically we have to determine both these beamformers, that is both your U bar and also V bar. That is, remember, normally in a multiple antenna beamforming, when you have multiple antennas only at the receiver, you are simply determining a single beamformer, that is beamformer at the receiver, that is what we have done so far. But here, because you have multiple antennas both at the transmitter as well as the receiver, one has to determine both the optimal beamformers, that is V bar, that is the optimal beamformer for the transmitter, and U bar, that is the optimal beamformer at the receiver. And these problems are interlinked, because depending on V bar, one has to choose U bar, and depending on U bar, one has to choose V bar. So, what are the optimal beamformers U bar and V bar that maximize the SNR at the receiver? That is the challenging problem that one has to address, which we will solve in the subsequent module. Thank you very much.